So let's take a look at number 103C. And this integral is going to be done via the tables of integrals. And there is a table of integrals that is included with our textbook. Got a printout copy down here that I'm going to be using. But I want to just take a moment to show you where those materials are located in Brightspace, and if you have the ebook, where those are real quick. So let me just stop share for a moment and open up the screen here. So I've got the ebook open and it's open into the tables right now. The way you get to that is on the side here, you go all the way down to appendices and formulas, open that up. And then the very last one is formulas, click on that. You can see I am way down. If you scroll all the way up, there's a lot of formulas. It begins with our basic algebra and trig help sheets that I normally give you, and then gets into the derivatives of the functions after the graphs of various functions, the differentiation rules that you learned in Calculus 1, and then keep going, and you eventually get to the tables of integrals here. They start with substitution and integration by parts, and then they go through the basic forms. You're expected to know the basic forms. I will not be given these these won't be given during any test. So numbers 1 really through 12, I expect you to be able to do tangent and cotangent. Even if you forget, you can rewrite tangent as sine over cosine and use the substitution rule to get this relationship. And then 15 and 16, I also want you to know the inverse sine and inverse tangent, the ones that evaluate as those antiderivatives. 13 and 14, I generally will give those to you, although I do show you how to prove the secant one in one of the lecture videos on trig integrals. Okay, but if you continue on, you'll see some other forms of various types involving trig functions. In fact, a lot of these trig ones are the ones that are in the shorter trig integral table in section 7.2 in the book. So at any rate, there are a lot of these. So we're going to be using these. The other location is in the course itself. Give me 1 second to make sure I'm viewing this correctly. So if you go into the content area and then over to course resources and help, there's the short table of trig integrals. The complete table that is in the textbook is here. If you actually have the textbook, then this might be like an insert that you can actually pull out. But this has all the integrals. And so this, or a portion of this, will be given on the test when I ask you to evaluate an integral using the tables. Okay, so let's see how this works then in this particular problem. Okay, so first of all, I look at this and, notice it's not something that we can do just by a simple substitution. If I let u be 4 plus x to the 4th, maybe, this whole expression, the derivative is 4x cubed, and I've got an x to the 5th up here, which leaves an extra x squared, right? X squared times x cubed is x to the 5th. And what am I going to do with that x squared? I've called u equal to 4 plus x to the 4th. Can I solve for x squared from that relationship? No, not really easily. So it's a little bit of a challenge. And I guess you could solve for x squared from that relationship, but it would still involve a radical. You wouldn't really get anywhere is the bottom line. And so we try and look through the table. Obviously, there's no trig functions in this at all, or other things. You might think of doing the method of trig substitution, which is actually one way to do this problem. You can actually use trig substitution, even though it's not x squared. You'll see what we're going to do very similar, but we're going to use the table, which the table these integrals in the table, a lot of them, especially like forms involving the square root of a squared minus u squared, these forms in this table were derived or can be derived by trigonometric substitution. So it's just they've done the trigonometric substitution, so to speak, for you. When I look at the forms in this case, my form, I see the square root of 4 plus, it's x to the fourth, but I can think of x to the fourth as being x squared, and that's what I'm going to do here in a minute. But so I'm thinking it's a squared plus u squared form. And so I go through the table and look for that form. Here it is. And I try and find, you might say, do I go ahead and look and find one that matches my integral that's given here? Well, you want to go ahead and do your substitution for u before you do that. I don't see anything that has, a u to the fifth or, anything like that just by looking. So I'm not quite sure which one of these, if any, is going to work. I don't know. It's not a guarantee I'm going to find something that works. This list that we have of integrals has 111 total ones, but I have books that have, hundreds and more, thousands of integral forms. And so, this is just a representative. But this one actually is going to be doable. And the idea then is, like I kind of hinted at, is, we've got this x to the fourth. I really want that to be u squared. I know the a squared is 4, so that tells me a is 2. And then the u squared, I'm going to let be x to the fourth. That means that u is actually what? X squared, because if I square u, squaring x squared gives me x to the fourth. Okay, and very important here, often forgotten, is the du. You have to have that du. In this case, the du is 2x dx, and that's going to help us transform this integral into something that will match up in the table. I like to have everything changed. I replace the 4 with actually a squared, so it looks exactly like the integral forms in the table. So let's do that. What about this x to the fifth? I've got a 2x dx. Well, there's x to the fifth. Well, go ahead and solve for x dx by multiplying both sides by 1/2, right? So x dx is 1/2 du. And what I'm going to do is then rewrite my original integral. X to the fifth, I'm going to split up as x to the fourth times x dx. Why did I do that? Because my x dx is going to become 1/2 du. You say, well, what about the x to the fourth? Well, good news, because this one's going to work. We've got what? X to the fourth is what? U squared. Okay. Again, these integrals that we have are contrived in a way that, if I ask you to use the tables, it's going to work. But in general, if I just give you an arbitrary integral to do, a substitution may not give us one of the forms in the table. But this one will. And so, now I just do a complete substitution, right? So x to the fourth is what? U squared. X dx is 1/2 du. And the square root of 4 plus x to the fourth is going to be square root of a squared, 4, plus u squared. Okay. Pull that 1/2 out, and here's what I have. Now I look in the table for this form. And if I look in the table for this form, guess what? I find it when I get to number 89. It's identical to that one. This factor of 1/2 is important. And that's often the case. You need to make sure that you do your du and match everything up. Okay. Because a lot of times there's some constant multiple out here. But this part, this is where we're going to use the table. So making use of the table, which again, this formula in the table probably came from a trigonometric substitution. Okay, but we're going to make use of that. And I like to just go ahead and just copy. I'm just going to copy down exactly what's in here in terms of u and a. And then I also indicate the number of the integral when I use it. So in this equal sign, I'm going from this integral to the form from the table. I go ahead and tell what number I'm using. And I'll usually ask you to do that on the test or something. If I give you a table, give me the number that you're using. So there it is. Now I just replace, if you remember, u was equal to x squared, right? U squared was x to the fourth, so u is equal to x squared. A is 2 and a squared is 4. So I'm plugging all those values in. I get u divided by 2, which is the same as 1/2 u. So I write as 1/2 x squared. You can write as x squared over 2, same thing, right? Since u is x squared. I get a squared is 4, u squared is x to the fourth, right? U is x squared, u squared is x to the fourth, minus a squared is what? 4. Yeah, a squared is 4 divided by 2. So I should actually have a 2 here. Should have a 2 here, sorry. Did this one beforehand to make sure everything came out perfectly right, and I missed something. Yeah, a squared is 4 divided by 2, so there should be a 2 here. Oh, I know. I've totally forgot my 1/2. That's my problem. I had a discussion with another student about this, that I sometimes forget my constant multiple as well. Okay, so I do need to distribute that 1/2 through, which is going to change what I have down here. Sorry about that. So 1/2 u squared over 2 is 1/2 x squared. So times 1/2 is actually going to be 1/4 x squared. Sorry about that. And then here, a squared is 4 divided by 2 is 2, but then times 1/2 is 1. So that part's correct. The u is x squared, and then plus the square root of 4 plus u squared again being x to the fourth. So I've done all the transforming back to the original variable, and there is the result. Okay, so again, the point is, don't try and just look at the original integral and try and match that up with the forms in the table. Do your substitution, right, that you think will work, right? Go ahead and do that. Transform everything from x's over to u's. I even changed the 4 to an a squared. I like to do that just so it looks exactly like the ones in the table. So you get it exactly like that. Then you can rewrite it using the formula given, and then change back to the original variable. Okay, hope that kind of helps how we do ones involving tables of integrals.